Understanding physics, hard bits, kinetic theory equations. What we're going to talk about in this video is this bit of the specification here. Some pretty chewy equations, all bits and pieces all over the place. So this one in particular, PV is a third NM CRMS squared. Where does that equation come from? It doesn't come from experiments, it comes from a model, kinetic theory. What can we calculate using it? What are all the bits in this equation here? What's this CRMS? What on earth is that then? Talk about that, tell you what that means. Do you need to be able to derive it? According to the specification, yes. Although you won't be asked to start from scratch and derive it from scratch, but there's loads of bits and pieces in the derivation that you will need to understand to show that you can understand it. That's what I'm going to do. I'm going to derive this equation and you should be able to follow it. Yeah, all the different steps that I'm going to take. And so this equation is going to come from a mathematical model. And that mathematical model is called kinetic theory. Kinetic theory is a model of a gas, okay, of an ideal gas. Now, real gases, like the air in the room that you're in, they behave pretty much like an ideal gas. Except at very high temperatures, very high pressures, real gases behave like ideal gases. Okay, an ideal gas, you should know, is one that obeys Boyle's law. That's the definition of an ideal gas. But anyway, kinetic theory is a mathematical model. And what is this model? It's just a load of balls bouncing around inside a box. Yes? And if we think of a gas, imagine a gas to be lots of little balls bouncing around in a box, then we can use Newton's laws of motion, we can use conservation of momentum, we can use whatever, we can work out an expression for the pressure of a gas. Okay? We need to simplify our model. To do that, we need to make some assumptions, and you need to learn these assumptions. Okay? Very important, there's a very large number of particles moving randomly. A ridiculously large number of particles moving randomly. They are perfectly elastic spheres. Elastic in the sense that kinetic energy is conserved. Yeah, perfectly elastic spheres. We ignore interactions between the particles. Now, the particles do interact with each other, actually. In real life, your air molecules are banging into each other all the time. Many, millions of times. In fact, if something like 1 billion times a second, it's a ridiculously big number. But that doesn't affect our calculation, okay? We ignore the interactions between the particles. And then the last one is to do with the time of the collisions. The time to collide is negligible compared with the time between collisions between the walls. Learn 2 or 3 of them. Learn the first 3. Yes? This is a very, very common exam question. Explain in terms of the motion of the gas particles, how the gas inside this balloon exerts pressure on its inner surface. If you've read the question in terms of the motion of the gas particles, it wants an answer where you're waffling on about the particles hitting the walls. And the answer you should write down is something like, every second, a very large number of gas particles collide with the wall. Their momentum changes, and so they exert a force on the wall. Yeah, the wall exerts a force on them. From Newton's third law, they exert a force on the wall. From Newton's second law, F equals delta mv over t. The change in momentum over time tells you what the force is, and then pressure is force over area. Learn that. Very, very common. Very often there's another part, which is why is the pressure bigger at higher temperatures? Let's not worry about that for the moment. Okay, basically what causes this pressure? And so you've got a very, very large number of particles banging into the wall. Bang, 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 bang. It's a little bit like rain landing on a roof. Okay, now each collision is a little force against time, little bump. What we're going to do is we're going to work out the average force. And if we know the average force, we can work out the pressure. So how are we going to do it? Well, here we go with my derivation. So imagine a ball just bouncing in one dimension, and it hits that wall, and then it goes over there and it hits that wall, and then it comes back and it hits that wall again. Imagine a particle of mass little m. Let's say that its velocity is u, yeah, and that's in the x direction. So the velocity of this particle is u in the x direction, and it's inside a cube, and the cube is sides L by L by L. So in one dimension, traveling with a velocity u, and every time it bangs into that wall, this wall here, call that wall x, so that's this wall here. Every time it bangs into that wall, its change in momentum is 2mu. Now, why is it 2mu? Because it's mu minus mu, yeah, which is 2mu. If you like, if it just stopped dead, then the change in momentum would be mu. But it's actually double that because it comes off with the same speed. So it's 2mu is the change in momentum. The time between collisions. Because it travels a distance of 2L to get there and back, then the time between collisions is 2L over u. That's just u is velocity is distance over time, and I've rearranged it. So t is 2L over u. So the average force due to one particle hitting that wall at right angles is delta mv over t. So that's the change in momentum divided by the time between collisions is mu squared over L. So that's the force due to one particle, mu squared over L in one dimension. And then the pressure, just divide that by L squared, because the area of that wall is L squared, and that gives me mu squared over L cubed. Starting to look a little bit familiar now. Okay, let's fiddle with it for a bit. Now, there are n particles. There's a very large number, big N. So I'm going to multiply it by big N and use the average value of u squared. Yeah, because they've all got different values of u. So the average value of u squared, and then times n, because n is a very large number. And then L cubed, I'm changing that to V, because L cubed is the volume. It's a cube of sides L. So we are up to this, PV equals NM U squared bar. U squared bar is the average value of U squared. We're still only in one dimension. We've got to get three-dimensional. Okay, so we're not going to be using U, we're going to be using C. Now C is the velocity of a particle, and there's lots and lots of particles, so C1, C2, C3, C4, all the way up to Cn. The box contains a very large number of particles moving randomly, and because of that, the average velocity is going to be 0. Yeah, C bar, the average velocity, will actually be 0. So the average velocity is useless. So we don't use the average velocity. What we use is, it's called the RMS velocity. It's the root mean square velocity. What you do is you get all your velocities and you square them, and that gets rid of all the negatives. Then you get the average value of these squares, and then you get the square root of that. So it's the root of the mean of the squares. And it's equal to, roughly equal to the average speed. So the average speed isn't 0, yeah, the average velocity is. And that's what CRMS is. It's the root mean square velocity. Okay, you can write it as CRMS like that, as AQA do, or OCR, it's the root mean square, so root C squared bar. yeah, the root mean square velocity, roughly equal to the average speed. Okay, think of it as the average speed. Now, where does the third come from? Well, because there's a very, very large number moving randomly, in the x direction, we've got u squared bar. In the y direction, you could call it v squared bar. In the z direction, you've got w squared bar, whatever. But the point is that they will all be equal to each other. Because there's a very, very large number moving randomly, yeah, those three are equal to each other. And then from Pythagoras, yeah, that plus that equals c squared bar. Yeah, just Pythagoras in 3 dimensions. Therefore, u squared bar is a third of c squared bar. U squared bar was the average value of u squared in 1 dimension, and now we've got it into 3 dimensions. We're back to c, which is our 3-dimensional c, but we've got this third. That's where the third comes from, to go from 1 dimension to 3. So PV is a third NM c squared bar, yay. Or PV is a third NM CRMS squared. It's the same equation. Now, this equation is useful because it works. We got this equation from kinetic theory. We got this equation from a mathematical model. But it actually works. We can predict the behavior of real gases as long as they approximate to an ideal gas. Yes, we can predict the behavior of real gases in everyday life using an equation that we got from a mathematical model. What does that tell us about the mathematical model? It tells us it must be pretty good. It tells us that real gases in real life, maybe they are made up of a very, very large number of particles bouncing around. Yep. Now, this is an equation that I actually had to learn many years ago when I was a sixth form student. And it's basically another form of the same equation. Now, N is the number of particles. Little m is the mass of a particle, so Nm is the mass of the gas. If you like, we could call that big M, the mass of the gas, yeah, is Nm. And if you divide that by volume, that gives you the density of the gas. And so our equation becomes CRMS is root 3p over rho. Yeah, that's the equation I used when I was a student, root 3p over rho. Now, do that then. The density of the air in the room you're in now is about 1.2 kilograms per meter cubed. The pressure is about 100 kilopascals, yeah, about 1 bar, 1 atmosphere. Calculate the RMS velocity of the air molecules. What's the average speed of the air molecules in the room that you're in now? Before you work it out, guess what it is, then work it out, and is that surprisingly big? About 500 meters per second. Yeah, and that's the average speed. Yeah, the RMS, the root mean square, is the average. Okay. What are these groovy things going on down here? Well, down here, this first one is smoke particles under a microscope. And this is called Brownian motion. It was discovered in 1827 by a Scottish bloke, Robert Brown. And he actually looked at pollen grains in water. But why are the smoke particles? Why are they jiggling around and bouncing around? What is making the smoke particles do that? And it was in 1905 where a very clever bloke called Albert Einstein, amongst other clever stuff he came out with in 1905, explained Brownian motion in terms of air molecules banging randomly into the smoke particles. And it tells us a lot about the air molecules. It tells us that the air molecules must be moving very fast for them to have enough momentum, that the smoke particles are like thousands of times heavier than they are. And if they can make the smoke particle jiggle around, they must be moving pretty fast, and they're moving randomly, and there's a very large number of them. So this is direct evidence for our model of the gas. Okay, it's called Brownian motion. We can do some clever things with this equation here. Now we've got PV is a third nm CRMS squared. Now from the gas laws, we've got PV equals nKT. That's basically what we call the equation of state from an ideal gas. If you like, if you do chemistry, you might recognize, I'm sure you do, PV equals nRT. Little n is the number of moles, big R is the gas constant, and then T is your Kelvin temperature. Yes, and that equation comes from experiments. It comes from the gas laws. Yeah, the behavior of gases. PV equals nRT. Both of them are equal to PV. Let's put them together and we get that. So a third nm CRMS squared equals big NKT. The big n's cancel. Okay. Multiply both sides by 3/2 and we get a half m CRMS squared equals 3/2 kT. Now bear in mind that this CRMS is like the average speed. Now is that familiar? A half mass times speed squared? What's that then? I'll tell you what it is. It's the average kinetic energy. The average kinetic energy of the particles in the gas equals 3/2 kT, at least for an ideal gas. Yeah. So the average kinetic energy of the particles in the gas depends on one thing and one thing only, and that is the temperature of the gas. Okay, so we can say now we have like a definition of temperature. What do we exactly mean by temperature? Temperature is a measure of the average kinetic energy of the particles. Okay, and if that's the average kinetic energy of the particles, if we multiply that by the number of particles, that will tell us, yeah, oh, by the way, before I get into that, these are just different forms of the equation. You should know that Boltzmann's constant is just the gas constant divided by Avogadro's constant. It's a combination of constants. Okay, and bearing that in mind, these are just, you know, the same thing. Obviously this one here is a lot more convenient. Yeah, 3/2 kT. Going back to what I was saying a second ago before I rudely interrupted myself, if you multiply the average kinetic energy by the number of particles, that will tell you the internal energy of the gas. Yeah, the total kinetic energy of the particles. Yeah, the internal energy of the gas. If you multiply that by n, you will get the total internal energy. Do you remember kind of first law of thermodynamics and all stuff? Assuming that it's an ideal gas. Here's a couple of questions that you should be able to do. First one should be very straightforward. Do it yourself, work it out, and the answer is that, and it's just 3/2 kT. Yeah. Make sure that T is in Kelvin, so it's 293 Kelvin. Second one's a little bit trickier, but you really should know it. It's a very common kind of multi-choice question. This one here, this balloon contains air at 20 degrees centigrade. Air is mostly a mixture of nitrogen molecules and oxygen molecules. Which type of molecule will have the greater kinetic energy? Which type will have greater average speed? Well, now basically, which will have greater kinetic energy? And the answer is it will be the same. Why? Because the average kinetic energy is 3/2 kT and they're at the same temperature. Which will have a greater average speed? And that will be the nitrogen. Now why? Okay, because nitrogen molecules, N2, yeah, they have a relative molecular mass of 28, don't they? Your oxygen molecules, which is O2, they have a relative molecular mass of 32. So they are heavier. If they have the same average kinetic energy, that means that on average the oxygen molecules will be slower because they have a bigger mass. And how much slower? Because it's a half mv squared, it'll be root 28 over 32. Yeah.